washing water or fluid that's coming to separate the particles. And what this is going to do is it's going to harvest the red particles from the fluid through acoustic focusing, and then it's going to collect them over here, and this will be channeled to the spectrometer. I don't see very well, but you see any particles moving in there? No? Okay, I lost my mouse again.
Not working.
Well, I hope to be able to, in the interest of time, I'll skip it, but to show it to you is very impressive. As soon as you turn the acoustic field off, then the particles start collecting in the channel. They are being washed and collected and harvested. So I hope you can see the different levels at which this technology is being implemented and is being developed. We're putting no stops, whether it is fundamental fluid mechanics and acoustics, centrifugal fields, scattering phenomena, you name it. We want the problem solved. And we want the problem solved in a reasonable length of time to make a business, right, and have a profit. But also we want to develop the science and the understanding of the processes as we move along. Okay, now from the software point of view, we're using standard scattering theory, and again, I need to make sure to review the equations. This is the let's say, the transmission equation that relates the number of particles, the scattering efficiencies, the particle size distributions for spherical particles, and it's a weighted sum of all the contributions from all the populations present in a sample. We use a variety of scattering models that have not been exploited to the extent that we have and that they can be exploited. These are very rich theories. They are nonlinear, and therefore they need to be explored carefully in the context of the problem that you're going to solve. So there is, again, ample opportunity to continue the development of these scattering theories and then the corresponding optical properties that are necessary as fundamental information to solve the problem. As I said before, these are more closely related to the materials science. These are related to electromagnetic theory. The optical properties, what is that we want to have? I mean, if you are going to address the issues of estimating optical properties, the first thing that you will notice is that your integrals grow from 0 to infinity. And it's very difficult to accomplish that from the practical point of view. So we need to devise both numerical methods and theoretical approximations that enable us to estimate self-consistent sets of optical properties over the range of interest for the wide variety of materials that this one deals with. But we have an advantage. If we have some understanding of the macroscopic properties of the materials, then by following these relationships, we can then get to the optical properties. If we have the optical properties estimated by other means, then we can again follow the reverse path and predict what our macroscopic optical properties would be from the point of view of the measurement. And again, there is ample opportunity, if you're curious on the math, to engage on these projects. The libraries of optical properties are built at different levels. They can be built all the way from the atomic and molecular level to macroscopic properties like what would be the absorption and refractive index of a suspension of red blood cells or bacteria. They include proprietary materials, in the case of industry, and proprietary material components. The advantages that we have is that now we have a complete set, not a complete, but a more complete set of interactions, and therefore a better set of optical properties that are permanent and they can be retrieved. So now we have the basis to continue to explore not only properties of materials, but also materials themselves. From the business point of view, we've been told this would be a very valuable contribution